The issue that I want to address is a challenge that was given to me in graduate school, a claim that I heard repeatedly throughout graduate school. The fossil order is explained by evolution. It's a claim that was made over and over again. I more or less cataloged it in my brain for the duration of my graduate school years. You don't have much time to rethink the things that you're being taught under those circumstances. I had a job to do, which was complete my degree. I tell that to students. Your job, your full-time job, is to learn. And that's what you're to do. You're not there to destroy the ideas of those you are learning under. You learn the tools that are necessary to accomplish what God has called you to do. And don't worry about all these other things. And definitely don't challenge your professors. They have the authority in the classroom to do whatever they wish to do. That is the authority given to them, and that's the authority you give to them when you pay money to go to college. So don't waste your time. Don't attack the professors. Don't do any of those sorts of things. For the duration that I was in graduate school, I accumulated the evidences for evolution. This was one of the big claims, and since my field is paleontology, fossils were important. Let's put it in a slightly different form, the proper form. What it basically means is that organisms appear in a certain order in the fossil record, which happens to correspond to the same order those organisms should have appeared by evolution. I've got feedback up here. Drop the volume down or something. A little bit painful. Sorry. We begin by testing that claim. Do not argue against positions if you haven't first determined if the claims are in fact correct. So we first have to determine if this is a true claim. Is there a correspondence between fossil record order and the order that evolution predicts? So in order to do this, it's not an easy thing to do. Basically, when I finished my dissertation in that summer before I started my first job, I sat down and addressed this particular issue, as well as several others, but this one was one of them that was premier in my mind. What you have to do to test this hypothesis is first determine what the order is that evolution predicts. Evolution doesn't predict an order a priori. It doesn't say, based upon what we understand about organisms, I would predict this would be the order of evolution. What you have to do is you have to determine from what we know about living organisms what the most likely order of first appearance would be if evolution were true. And that's not easy to do. In fact, I realized as soon as I started the project that no one had done it. No one had done it in evolution. And I've soon realized why. It's a really difficult thing to do. There's an enormous amount of information that must be gone through in order to do this, in order to produce what we call cladograms now in modern evolutionary theory. That's the mechanism or the means by which we determine the most likely branching order. I did this for all major groups, all classes, phyla, and kingdoms of organisms, from bacteria all the way through the things you're more familiar with. And this is a subset of it. This is only one part of the tree, specifically the plants portion of the tree. These groups, you're probably not familiar, you may not be familiar with any of the names on this thing. The Horneophytopsida, the Aglaophyton, the Rhiniopsida, Zostrophyllopsida. Most of these are extinct organisms. We've got a few Equisitopsida, that's the horsetails. We've got the Pinopsida, the pines, the conifers in general. The cycads, the Nidopsida are very, very rare in the present. Magnolia phyta are most of the plants. Those are the plants you eat. Those are the flowering plants. That's the big group. 250,000 modern species of Magnolia phyta. But these are all the major groups of plants that we know of from both the fossil record and the present. Now, the reason I've chosen this particular branch out of a much huger tree is that when I did this analysis for the entire tree, there was no correspondence between evolution and the the predicted order of major groups by evolution versus the order in the fossil record. The order in the fossil record is random with respect to evolution for 95% of all the major groups. So that's really all we have to say. Most scientists, we just say, okay, there's no prediction. Evolution makes no prediction that is fulfilled in the fossil record. If you can explain 95% of the data, forget it, go home. You've explained the data. So randomness is actually the major story. However, the 5% people get interested in. In fact, that's what everyone points to as evolution, as evidence for evolution, is the 5% that seems to correspond. And most of that is sitting in this group. The best evidence turns out to be the origin of the major groups of plants. And so that's what I want to address today, taking the best evidence out of that tree. And here's the idea. You produce an evolutionary cladogram, the most likely branching order. And notice the first group, Horneophytopsida, is the first one to branch off. So that should be the first group. The second group would be a genus, Aglaophyton, and then Rhiniopsida, and then two groups there, the Zostropholopsida and the well, I don't need to, obviously. You're not interested in all those crazy names. And there's a sequence then that they come in. And so I can put them in order, 1 through 9. That's the order predicted by evolution. Now we look at the fossil record order. And you have to understand the way paleontologists look at things. They're weird. They look at things weirdly compared to everyone else in the world. Most of you are familiar with timelines that start from the left and go to the right. The old stuff is to the left and the new stuff is to the right, and the time goes from left to right because you read from left to right. Chinese would probably do it the other way, but Hebrews would do it the other way, okay? For example, the opposite direction. In the fossil record, we go bottom up because the idea is that once a rock is laid down, it's kind of hard to slip a rock underneath the one that's already there. So typically the order of rocks is from the oldest ones at the bottom and the youngest one at the top. So paleontologists look at time from the bottom up. We're going upwards in time. So here is a representation of the fossil, at least the early part of the fossil record of plants. And we're looking at rocks sort of stacked up on top of one another. And the width of that green is the number of genera of plants that are found in that particular layer. So we begin with only one plant way back in the oldest rocks down there, and we increase in diversity of plants up through what is called the Paleozoic. So I'm focusing on the Paleozoic rocks, and then we can break this up into the groups that I was just referring to. So we got the Horneophytopsida down there, Aglaophyton is down there, Rhiniopsida, and so we have the diversity of each of these groups. And we can then go to the first appearance of each of those groups to determine the actual first appearance of these groups in the record. We can compare those to the prediction of evolutionary theory with the actual order. And you can see just by looking at it in general that it's fairly close. If you plot it, if it's a perfect correspondence between the order predicted by evolution and the order of first appearance, it should end up on that red line. It's very close. It's astonishingly close. And we're talking about 13 groups with an R squared of 0.98. 98% of the data is explained by that order. So evolution does, in fact, explain the order of the first appearance of major groups in the fossil record. So we've tested the hypothesis. The problem is that we do have a problem. Now, evolutionists would stop right there, and they do. They say, yeehaw, have a party. There's our evidence. Although I bet you have never heard any evolutionists argue that plants are good evidence for evolution. I've never heard it. I didn't even hear it in paleobotany class, where we study fossil plants. But it is. It's the most extraordinary and most impressive evidence for macroevolutionary theory on the planet from the fossil record. It's really quite extraordinary. However, the Bible would suggest this cannot be an explanation of the fossil record order. The Bible indicates that God, on the third day of creation, created the plants and created them all on one day. They would not be buried in a sequence that's reflective of the order of appearance, even if God did create them in this particular order. So there must be, if the Bible is true, there must be another explanation for the order of plants in the record. So given that I first tested the hypothesis was actually verified, that the fossil record order does in fact correspond to evolutionary order. The next thing is to find another cause for that. I'm going beyond what an evolutionist would do. Again, they would just pack their bags and go home and have a party. It forces the creationists, who aren't doing science, obviously, from the previous talk, to continue to do research and to look more closely at this issue. Going back to my cladogram, to the order of appearance predicted by evolution, I remembered in paleobotany class a major claim about plant evolution is that the story is a sea to land transition. The green plants are descendant, according to evolution, from the green algae, which exists in the ocean. So the plants evolve from ocean to land, sort of like the story of the vertebrates are supposed to be, coming from the fish to the amphibians to the reptiles, from the sea onto the land. The basic story of the evolution of plants is the same way. It's a really incredible challenge to design a plant. If you were given the challenge of designing a plant, the land plants present a huge challenge. We need for photosynthesis a presence of water, carbon dioxide, and sunlight. Well, the sunlight and the carbon dioxide are available on the land readily, but the water is not. The water is sitting at best in the soil at depth. That's not where the sunlight is. So if you want to do photosynthesis, you need three components that aren't found together on the land. In the surface waters of the ocean, they're sitting all together. We've got carbon dioxide dissolved in the water. We've got sunlight penetrating the water. We've got water in the water. So we've got all three components close together. Algae has it made for doing photosynthesis. But land plants have a challenge, especially when they get to be monsters, hundreds of feet high. The photosynthesis is way up there in those leaves, and the water is way down there in either the soil surface or maybe scores of feet beneath the surface. You've got to get water all the way. I mean, the design of plants turns out to be almost 100% for the purpose of fulfilling this photosynthesis requirement of getting water together with the oxygen, with the carbon dioxide and the light. And there's the challenge, going from plants that live in the water to plants independent of at least water in the immediate environment where they need to draw in, and in fact plants that live in deserts. And so we have a transition from organisms that live entirely in water to those who live outside the water, but they release sperm and egg that must swim through the water to fertilize each other, okay, for fertilization to occur. To ultimately things like corn, that you've got basically the sperm is sitting in a piece of pollen that flies through the air, lands on a plant, grows a pollen tube to the egg. The sperm swims to the egg, never exposing the sperm to the outside because it's dry. It's too dry. Things will die. If you see the incredible, remarkable designs. So knowing that this is the story, the evolution story of sea to land, I thought, well, what if we asked a slightly different question? What if you asked, what would happen, what would be the predicted order of plants if it was entirely arranged ecologically? Let's say you designed an ocean and land environment, such as the end of the half day of day 3. We have no land animals or plants, but we have just created the dry land. Now let's say we perfectly design organisms for the water, for the water-land transition, for the transition into drier and drier and drier situations. What would be the order, the plants would predictably be in if you just created a perfect situation. And here's the answer. Redoing the cladogram, not assuming evolutionary, not using all the characters, but only the characters that have something to do with survival in the immediate absence of water, what I call increased terrestriality. Now, I just transitioned from the previous cladogram to this one, and you might have missed it. They look very similar. Let's go back. That's the evolution cladogram. There's the ecology cladogram, the evolution cladogram, ecology, evolution. Notice there's a lot of similarity. Okay, if you take out all the characters that are not necessary for increased terrestriality, you end up with still something extremely similar. The ecological order, the perfect ecological order of plants from sea to land is very similar to evolution. In fact, if you do the same thing and put it down there, you get another very strong correlation between ecology and fossil record order, with an R-squared basically the same, slightly better at the third decimal point, but that's far too much accuracy. So plant groups actually appear in the sequence in the fossil record, which is consistent with both evolutionary theory and ecological order. So the next question becomes, what kind of a situation do we have in the present where we have that sequence of plants, from water-loving or water-requiring plants to fully terrestrial plants? Do we have a modern ecosystem that is like that? And what do the plants look like? And how do they compare with the plants that we see in the fossil record? And that immediately brings to mind an experience I had when I was 12 years old with quaking bogs. Now, some of you all might actually know about quaking bogs. Usually where I speak, nobody knows anything about quaking bogs. In the South, they don't have quaking bogs. How many of you have stood on a quaking bog, have visited and stood on a bit? 2 of you. Wow. Okay. You got more of a chance in the North, but alas, you haven't had the magnificent experience. At 12 years old, I went on a field trip with a graduate student who was studying these things, and he took a bunch of us kids out there. We got out of a car in southern Michigan and walked over a trail which went like this. And I was astonished in the Midwest that they had such verticality. This is crazy. I came from Illinois, flatlands is where I'm from, what I'm used to. Well, I learned later that what we were doing was walking over sand dunes. Sand dunes are created by the lake, 250-foot high sand dunes that have grown over by vegetation. And so we went on this path. It went up and down these 250-foot high sand, and they're very steep, and it was very tiring. And then at one point, I noticed, wait a minute, the path is flat, very flat. I looked back, and I could see behind me the flatness of the path, and then it goes straight up to that first ridge, and I said, wow, something really changed here. We got about 200 yards out into this flatness, and the guy leading us stopped and said, okay, everybody grab hands and create a big circle. Okay, it's a little weird. And he said, now everybody, what I want you to do is we got to get in this together. Everybody is to jump up and down at the same time and get into sequence. Well, that took a long time. We get a bunch of kids jumping up and down at the same time. But eventually, we figured out how to do the jump rope thing. Everybody jumps up and comes down in sequence. And I noticed, wait a minute, I lifted off, and it's a very strange feeling. But as I lifted off, I felt the ground leaving me going down as I was going up. And again, it took a while to get in the right sequence, but as we landed again, we landed on the ground, and then the ground continued to go down, and then came back up, and we left it, and then came back down, and the ground was going up and down. And the ground then, we're in a circle, so we create a circular wave in the ground that moves out away from us. The ground deforms in a wave-like pattern, and it's just awesome as you're looking across the people across from you in this circle. You see this wave moving through the ground, and the plants, the wave would get to the plants, and they'd go like that as the wave went through them. And it even got to the trees, and the trees, sure enough, did the same thing. Like, whoa! A series of concentric circles as if we had dropped a stone in the pond, and these water ripples were moving out away in circular fashion away from the center. Whoa! Mind-blowing. And I realized at that moment that we must be on a lake with a layer of vegetation or mat or something, and it was thin enough that we could move this thing up and down. This is a quaking bog. It's quaking. You can quake it. You can bounce the thing up and down. The theory of the quaking bog is as follows. And the glaciers came through. When they retreated, they left big chunks of ice in amongst the debris that was left with the melting of the glacier. These big chunks of ice melted, leaving a lake. So we have a lake. Plants then grow out from the edge of the lake towards the middle of the lake. And this is a picture of Bothell Bog in Illinois. It's the only remaining quaking bog in the state of Illinois. The only thing left in open water is in the very center, but you can see the original surface of the lake there. It's supporting in time a sequence of plants, from very short sedges and reeds to taller bushes to full forest and so on. When we got done doing our bouncing, we then continued our path. And as we went along, it eventually got to where you didn't need a group to do this. It got thin enough that individuals could create these really cool waves in the bog. And it got a little further, and I'm starting to worry. I mean, I'm a little guy at 12 years old. I didn't hit 5 feet till I was in junior in high school, so I was 4'10.5" and less than 90 pounds. So I didn't weigh a whole lot, but I still got to where I was really concerned because every foot you push the ground down. And then I realized that I'd better not be standing. Bipedalism is just not advantageous under this circumstance. So I got on my hands and knees to spread out my weight, and you could go a little bit further. And by now, we're no longer in trees. The trees have given way to tall bush cranberries and things like that. Go a little bit further, and we're now in short bush cranberries. And I feel I can't do the quadrupedal thing. It's now slug. Okay, so I don't want to, I'm thinking, pop through this, plump, and then you're underneath. Like, die. Okay, I'm never going to find my way back again. So I continued as far, and as I plied myself closer and closer to the ground, I'm looking at sphagnum moss and pitcher plants and sundew plants. This is really cool. This is every boy's dream. I wanted to have a room full of sundew plants and pitcher plants. Really, never could support them and take care of them properly. And here, I'm in the midst of them. It's just awesome. And then I could see further out where the thing becomes thin enough that there's no way that I could go any further. And there's even open water way out there. So you have this very thin mat close to the water, thickening as you go away from the center, eventually filling the entire lake. Now here's some actual photos from Bothell Bog. Okay, they produce a boardwalk over this, floating on top of the quaking mat. Now, in case you missed that, you just do that again. You actually can push down. This is close to the edge. A little bit further in, I'm pushing some ferns up and down, just to show this is real. It looks like ground, but there's some cattails there. They're firmly attached to each other, but they're in a floating, and a tree. There's one close enough. It's only about 4 inches in diameter, but it's close enough to the thing that I could move the tree back and forth, just to show. Bigger trees do the same thing, but they didn't have them close to the walk. And they wouldn't let us leave the walk for somewhat obvious reasons. the result of this is a diagram of the bog from the open water to the thickest part of the bog or up against the land. And you have at the outer edge open water, then a really cool region out there which you could only access with a canoe or something like that. And you realize that when you get there, it looks like there's a bottom only about 18 inches beneath the surface of the water, and you got little pollywogs running around on that. But if you stick your finger in there, it goes right through that. That's a false bottom. There's no real bottom there at all. It's plant material that's hanging beneath the surface of the water. Then you get into sedges and reeds, get into low bushes, and then tall bushes, and then full-size trees. And trees that are 2-3 foot in diameter, huge trees. Seems to be no limit to how big the trees can be, depending on as long as that mat is thick enough. The characteristic of these plants is increasing size and increasing terrestriality. The plants, obviously out at the edge, really need water. They can only exist in the presence of water. If it's dry like it is towards the middle of the lake, of the floating bog, they can't survive. So there's increasing specialized designs for living in drier situations as you move away from the water. And there's an increase in size. And that made me remember something about the fossil record of plants. This fossil record is not just an increasing terrestriality, which I demonstrated with that cladogram, but it's also increase in size. The Horneophytopsida are little plants. In fact, they don't have any leaves. They do all their photosynthesis on tiny, tiny branches. Aglaophyton, Rhiniophytopsida, Zostrophyllopsida, none of those puppies are any taller than about 12 or 18 inches. They're small plants. So you don't have trees until well up into almost the midpoint of that pile. So let's turn the puppy over where it probably makes more sense to you. Going from the older stuff to the left, younger stuff to the right, and increasing numbers of diversity, increasing numbers of different kinds of plants in each layer. If we reconstruct a bog from this, took the earlier bog diagram and take the plants that we find in the fossil record and draw them directly above, just go straight up and create a theoretical floating bog from this data. What we end up with is the concept of a floating forest. Modify it from a bog. It's not attached to the continent. It is floating forest. So we're looking at a half of the forest. Take that same photograph and flip it over. From one side of the forest, we got open water, goes up to the thickest part of the bog and full forest, and on the other side it goes back to open water. Given the volume of plants we're dealing with here in the fossil record, I'm saying this is a continent-sized floating forest. A continent-sized floating forest. So it's hundreds of miles wide and hundreds of miles in all directions. In the flood, such a floating forest would get destroyed by the turbulence of the flood. The waves of the flood would begin breaking up that forest from the outside in, first burying the plants on the edge, and then working its way in and destroying the plants in sequence. Thus, you would produce fossils of the Horneophytopsida earliest, and then the Aglaophyton. As we move in, they would stack up in the ecological order that they were growing before the flood. So, when you go to a museum and you see reconstructions of the past life, they're taking various snapshots of these different layers and saying, this is really old life, this is less old life, this is even less, this is newer life. But I'm suggesting that they're all snapshots of the same moment in time, but we're looking at snapshots from the edge of the floating forest towards the middle. So the early Devonian landscapes are actually a reconstruction of the edge of the floating forest. Here are the Rhiniophytopsida there, Zostrophalopsida, and we're looking out toward, forget the mountains and stuff, as imaginary. Mountains aren't fossilized with the plants. So you're looking out to open ocean. So we're standing on, probably in a very bad place for us as bipedal organisms. We wouldn't be able to stand out here. But if you looked across, this is what the edge of the floating forest looks like. So when you go to a museum and look at these beautiful dioramas, just reconstructed it, you're looking at the floating forest at various stages, walking from the outside of the forest towards the middle. So that's on the edge. Then we have the coal forests, what are called the coal forests. These occupy the middle of the beautiful dioramas that are found, for example, in the Field Museum in Chicago. These represent the center of this floating forest. Now, looking at, again, this sequence of plants and how they're piled up in the fossil record, it's an increase in size and terrestriality. This floating forest theory explains both of those things, but it goes further than that. It also explains why these plants are largely extinct. You didn't know about the names of these plants. You'd probably never heard of these crazy plant names. Why? Because they don't exist in the present, or very rarely. You have thousands of species in the past, and we only have scores of species of these things in the present. And the reason for this is that the ecosystem that God created, the floating forest, could exist if God created it on the ocean, but it could never recover following the flood. You could never regrow the floating forest with the roughness of the seas and the oceans following the flood. So the poor plants that existed as a very happy ecosystem, my roommate in college from Brooklyn, New York, called everything that he liked happy. So I'm going to use that term. I thought that was kind of cool. The happy plants that existed in the floating forest before the flood could never recreate that forest following the flood. So all they could do is make the best they could in a world that wasn't designed for them. And so very few of them survived to the present. So it explains why these plants are near extinct. It also explains another feature that I wrestled over for a long time when I was in graduate school, when I was out on field trips. We're finding these beautiful plant fossils, and I'm saying, but they're found in marine rocks. These are terrestrial fossils, so they argued. They must have been from the land because they're land plants, but they're found in marine sediments. Well, that's because they wash out to the ocean and get buried in marine. How many land plants are found off the beach, buried in the sediments offshore? It just doesn't happen very often. And I was used to finding millions upon millions of plants in some of these deposits, beautifully preserved, but in marine sediments. I struggled for a long time. I didn't understand. How could terrestrial plants be in a marine sediments? This explains it. This is not a terrestrial ecosystem. This is a marine ecosystem. Sure, it's floating on top of the ocean, but it's an ocean ecosystem. That's why they're buried in marine sediments. Also, it seems to explain the strangeness of some of these plants and the weird plants. These trees are hollow. They're all hollow. None of them are solid. We're used to trees with what's called secondary wood. That stuff, if you take the bark off and take that living layer off, which is very, very thin, then most of the tree is this dead wood, secondary wood. It has a very important function, but it's occupying the center of that tree and most of the mass of the tree. These things, none of these, all these big, large trees found in the fossil record, all of them are hollow. They're made of layers of bark, and there's no secondary wood. That's kind of strange. Why? How? I mean, first of all, the design of a 100-plus foot tree that's hollow. That's pretty cool. Furthermore, the strange roots, or technically they're not roots, they're called rhizomes. They're hollow. Hollow roots? How do you grow a hollow root through the ground, through soil? without it collapsing. That's not the worst part of it. Coming off of the hollow rootlets, hollow roots or rhizomes, are these, they're the size of straws. Very soft and flexible. You can tell that from the fossil record. They just kind of, they're very clearly very soft and flexible. Hollow, soft, flexible structures that come off of the main root at 90 degrees to the root. You've pulled enough roots or whatever that you know that most plants don't have roots like that. They have roots that kind of look like the tree in the ground, where big root branches into smaller roots at something, at an acute angle, okay, and keep branching like that. These things are hollow, with hollow structures coming out perpendicular to them, like and this is weird. There are some plants in the present with this structure. They're all little itty bitty plants, and they're all aquatic plants. They all float. The reason for the hollowness is so that they have air inside and they can float in the water. Cool! Okay, that's really neat. What a better design could you imagine for a floating forest than to have full-size trees that are designed to be light and designed to float? And in fact, this led Joachim Scheven in Germany to claim that just focusing, he's not looking at all the plants, he's only looking at the coal plants, the coal trees. Because of their hollow structure, because of this rootlet structure, he hypothesized back in 1981 that these represented a floating forest. Again, he wasn't looking at the whole picture, I was, and I didn't know about this at the time I generated the floating forest hypothesis for all the plants, but his theory fits very beautifully into the larger floating forest theory. Also, we have the issue of coal. Let's see, technically I'm out of time. The old theory, the conventional theory for the origin of coal is the swamp theory. The idea here is that plants living in swampy conditions that we know of in the present drop their leaves and branches and that sort of thing into the water. The water does not allow for full decomposition of the material. It accumulates and produces thick layers of peat in those swamps. And the idea is that that peat is then ultimately made into coal. And so the conventional theory that you will usually hear in geology classes as to how coal came to be is by these kinds of swamps. Now, I had problems with this hypothesis when I was in school. Some of the problems I have is kind of typified by my caricature of a coal seam. Coal seams are, imagine these rectangular boxes extending out as black layers and representing a layer of coal. Characteristically, coals have a very flat top to them, very flat. And you go into a coal mine, and you've got typically a flat ceiling. They've taken out all the coal, so what remains is a flat ceiling. I sort of thought that that was because they carved out a flat ceiling. No, that's because the coal seams are almost invariably flat-topped. But they're also flat-based, giving a flat surface at the bottom and at the top. And they have these things called benches. They're called benches because if you take the coal off the top of the bench, it leaves a flat surface and you can sit on it on top of the lower ones, so it's a bench. These benches separate coal seams with layers of shale. Now, the thickness of these benches varies from about 3/8 of an inch to several feet sometimes, separating two portions of a coal seam. The benches are thin and again flat-topped and flat-based and containing marine fossils. Okay. And then inside the coal, looking at the petrography of the coal, looking at it under a microscope, you can actually identify plant parts. They're large enough chunks of the original plants that you can actually identify the bark. In fact, that's what most of it is made of. At least the Pennsylvanian coals of the eastern United States are almost entirely made of bark. And if you look at the bark in macroscopic view, you realize that you can trace these pieces of bark in such a way that there's chunks of bark that are about dinner plate sized, typically. And so it's mostly a bunch of dinner plate sized chunks of bark making up coal. Well, there's several real problems with this hypothesis. I wondered about the flat top stuff. I said, I grew up in Illinois. I didn't grow up where there were swamps like this. So I asked, how do you get a flat top to the coal? Because you got this swamp, big trees dropping stuff down, that accumulates your organic matter, but then the trees are in the way. How do you get a flat surface? How do you get the trees out of there? And they said, well, what happens, this was their answer to me, they said a hurricane comes through and levels it off. Well, I was stupid. I came from the Midwest. I'd never experienced a hurricane. I didn't know what a hurricane did to a forest, a swamp like that. So I gullibly bought it, although I was a little suspicious. Then I had opportunity on a field trip, also in college, to a wonderful opportunity of seeing an area just after a hurricane. Geologists love catastrophes. And it was a really cool situation. There was a coastal swamp in South Carolina that was hit by Hurricane Hugo. And it's really great. I mean, this swamp was right close to the coast, and the hurricane just blew that swamp away. Actually, it didn't blow it away completely. It dumped it on a town. Mud. I mean, all of that stuff in the swamp ended up on the town. It was just awful, great stuff. I really enjoyed it. But the forest that was destroyed, I stood in awe of the power of the hurricane. But the other thing I observed was it weren't flat. There was nothing flat about that. You've seen pictures of hurricanes and tornadoes coming through an area, and even F5 tornadoes don't leave it flat. They got trees stuck up. They break a tree off, depending on its diameter. It depends on where it gets broken off. Big trees either are uprooted altogether, and then you got the roots sticking way up in the air. Or if they didn't get broken, if they didn't get uprooted, then the tree breaks off. If it's really big, breaks off way high. Smaller trees break. I mean, it's really rough. And then there's limbs, and you couldn't walk through that thing. I couldn't walk through it. It's like, this ain't flat. How do you get flat coal? And it's even worse to think about the benches. Okay, let's assume, for the sake of argument, I don't know how, but let's assume there is a lawnmower that could shave off our swamp, nice and flat, just the way we want it. Whew, yeah, we got it. Okay. Now, we got some mud come in. 3/4 of an inch of mud comes in. Somehow comes in from the ocean with marine critters in it, but then it recedes. Okay, fine. Now, let's rebuild our swamp. But don't you dare disturb that 3/4 of an inch of mud. I can't do that. I don't understand. I can't do that. How do you do that? No one could answer this question. And furthermore, just thinking about it, and I'm the theoretical person. I'm not so good at making things work. I touch something and it breaks. And so I got to work on theory, and I'm thinking, what about the bottom of this thing? How do you get a flat surface on the bottom? These trees are dumping material in, but their roots are reaching into the material underneath. I would expect to find the trees traceable into the mud underneath. But no, the trees are sitting on top. I mean, this is really weird. let's see, that thing. Okay, it'll eventually, on top of the coal. I don't know, it doesn't seem to be, I got too big of fingers. See, I can't touch anything. Okay, forget that. On top of the coal, we've got these root structures, big things, 2 feet in diameter with roots. And the whole thing's sitting on top of the coal. The roots aren't going into the coal, they're sitting on top of it. And this creates real problems in coal mines. It's what are called widowmakers. You go in and you take out the coal, and what you have are these, you look up in the ceiling, and there are these roots, stumps. They're above the coal. They're hollow, so inside the stump it's full of sand. It's a sandstone column that's sitting right over your head. Zoomp! Widowmaker, okay? These things are all over the surfaces, the tops of caves. Of coal mines. So it's upside down. Something's wrong here. It should be that the roots are down below, that the stumps are in the coal, below the coal, but they're sitting on top of the coal. I'm so confused. So anyway, enter Steve Austin. This is a picture of Steve Austin before he got married and became more conservative. And he's examining a drained coal swamp in Nova Scotia. And this is a perfect, if the idea of a swamp is true, then this ought to be a perfect example. They drained a swamp and then cut through it. And there you've got that layer of peat from Steve's hand all the way up, sitting on top of rock. And as Steve describes it, it's organic material. It's obviously broken down plant material, but it's got the consistency of coffee grounds. You can't find identifiable plant structures like pieces of bark, dinner plate pieces of bark. No. It's decomposed to such an extent that you got tiny little fragments of organic matter, and you can't identify the individual fragments, except for those white things. What are those white things sticking out? Roots. Not of dead plants, but of plants that were alive at the creation of the... So it's the only identifiable plant structures are roots. But that's not what you find in a coal. You find pieces of bark and no roots. So I'm still confused. Okay, so Steve Austin went to the University of Pennsylvania, Penn State University for his dissertation after being at the University of Washington here as his undergraduate. And he asked his advisors to show him the best example of a coal created by the swamp hypothesis. And they directed him to the Kentucky 12 coal in western Kentucky. The problem was that when Steve investigated that coal, he found these characteristics: the flat top, 2 benches sitting in it, very thin benches that are traceable across counties, flat base, bark chunks, and it just didn't work. He couldn't make the swamp hypothesis work. So he says that he was sitting in his bathtub playing with the bubbles one day. Yes, graduate students do that too. Most of our ideas come in the shower if we shower, and bathtub if we bathe in the bathtub. And he conceived of this concept that the trees, remember they're hollow, that the tree logs were floating around in water, and they rolled against one another, peeling their bark respectively off of the logs. The bark would become waterlogged and fall down to the bottom of the body of water and accumulate as piles of bark. Now this is really neat, because if the bottom of this body of water was flat, then the pile of bark would have a flat base. And if the log mat was blown around and blown out of that area for a while, then the surface would be flat, where the bark was laying, and then mud could come in, 3/4 of an inch of mud can come in from a marine source, and then the log mat could float back over, be blown back over, and continue deposition. and go away again, leaving a flat top. You could explain the flat top, flat bottom, the benches, the dinner plate sized pieces of bark. Everything is beautifully explained by his log mat theory. And in fact, Steve Austin successfully defended his dissertation in 1979 to argue that this is how the Kentucky 12 coal was formed. And given that every coal seam I've seen has the same characteristics, I think his theory explains probably the origin of all of the Pennsylvanian coal seams. Now, what's cool about Steve is there's a whole bunch of things that happened in his life which are just purely supernatural timing. He defends his dissertation in June of 1979. In May 18th of 1980, less than 1 year later, an event occurred which gave him a field test in the sorts of his theory. Less than 1 year later, Mount St. Helens blows up and covers Spirit Lake with over 1 million logs. Now, these logs are different than the logs we're talking about here. They have secondary wood, but they do have bark on their outside. So that wood would roll against other pieces of wood, and the bark that was on the outside would theoretically fall down to the bottom of the lake. Well, here's a picture of the lake in 1991. I took that picture in 91, and all of the bark is gone from the logs floating on the lake at that time. Well, Steve had to go down to the bottom of the lake and find out if there really is a layer of bark at the bottom of the lake. Not something you tell your mom about. Because in 1980, the mountain is still active, and 6 different times it blew its dome into and poisoned this lake again. And plus, you got to go down into 38-degree temperature water. The visibility is about 10 to 12 feet, 12 feet at the very best. It's about 40 feet deep at the shallowest, so you're in absolute darkness with much less visibility than you're supposed to have diving. Just isn't right, okay? And furthermore, you go down, and the log mat blows over the top of you, and you've got 3-foot diameter logs rolling up against one another. You're dead meat. You can't get out of that situation. I mean, everything is just what a guy would want to do, but never tell his mother. Sure enough, he went down to the bottom of the lake, and there is in places 3 feet of bark at the bottom of the lake, seemingly verifying his theory. Now, as soon as I introduced the floating forest hypothesis, he was quick to remind me, this is not my idea. He said, my idea was floating logs. I said, yes, Steve, I know that. But your floating logs are a result of destruction of the floating forest. After the flood had destroyed the entire forest, all that remained were the floating logs. The last part of that sequence would be these logs, which would then create the coal seams. And so the floating forest explains where the log mat came from. The log mat theory of Steve Austin explains how that produced the coals. It explains why, when you follow these coals, they laterally move into marine sediments. You follow them long enough, and it turns right into marine sediments, which fits of course, the floating forest hypothesis. Also, the fact that C14 dates on the coals are not infinite. They're giving ages of thousands of years. The biomass of the coal suggests you would have to have a forest the size of a continent to explain them, but the floating forest, in fact, gives that explanation. The geographic distribution. These coals are found from westernmost Russia all the way across Europe, and then from easternmost United States all the way into Missouri and so on. Eastern United States is covered with them. Europe is completely covered with them. The ocean in between not. And that's when the two continents were together. And the coal seams, 120 coal seams in Illinois Basin alone, all with the same exact fauna and flora. The critters and the plants on all the coal seams are exactly the same species. Did my dissertation on among other things, a brachiopod, or brachiopods, the Lingula genus of brachiopods. Lingula squamiformis and Lingula middleoides are two Lingula species found from the base of the Carboniferous to the top of the Carboniferous. Zero change in the morphology of those species for what geologically is thought to be what conventional geologists would say is 100 million years. The coal forest supposedly dominated for 100 million years of time, but not a single species changed in that entire duration because it's from the same forest. It's also a repeated sequence. You've got the mat flows back and forth. It produces the same sequence of deposition over and over again, the unchanged biotic distribution. So the floating forest theory explains also something else. This came as a complete surprise to me. It dawned on me one day, what about the critters? I almost forgot the critters. I got to remember, what if I was on that floating forest? I remembered it wasn't a good thing to be bipedal on the edge of that forest. What if God created a floating forest and he wants to put critters on it? What kind of critters would he put on that perfect forest? Well, what kind of a critter would he put on the edge of the forest where any one of us would crash through? Optimally, you'd have an organism that didn't support its weight on the mat. Floated, could support its weight in the water, but had legs to run around on the mat under the water. That's a weird critter. That's like a fish with legs. And that's what Aglaophyton, well, that's the genus of, these are the plants. Tiktaalik is a fossil in the record that is a fish with legs. He doesn't have lungs. He can't come out onto the land. He is a fish, but he's got legs. Why does he have legs? I think he has legs so he could run around on that submerged mat on the edge and won't fall through because he can support himself. Perfect design. And guess what? Where is he sitting in the fossil record? He's sitting with the plants that would be in that section of the floating forest. So the flood first is burying fish, and then a fish that looks like a half fish, half land animal, and then amphibians. This explains the sequence of transition from fish to reptiles. It's just magnificent. Look at that little guy. He's got weird fins that are legs. He's well designed for this. So, in the end, floating forest theory explains the things evolution does. Evolution explains just as I started out with, it says the order of the fossil record is consistent with evolution. Yes, for the plants it is. Evolution explains all these things. It explains the increase in plant size, the increase in terrestriality, the fact that Paleozoic plants are near extinct because they lived so long ago, they've gone extinct since then. The sequence of intermediates between fish and amphibians, it explains those things. Good job, evolution. Floating forest theory explains those and a bunch more things that evolution can't explain. It's a better theory. It's also synthetic theory. It took Steve Austin's floating log mat hypothesis that he'd already developed and incorporated it into a larger theory. It took Joachim Cheven's theory of the anatomy of the plants and pulled it into a larger, more synthetic theory. It's also heuristic. The theory makes predictions about the fossil record and allows us to do further research into the fossil record of the plants. So this is, I'm laying this out as an example of how creationist theory should be built. Even though it's not science and has nothing to do with science and pseudoscience, what we do is evolutionists would have stopped. They did stop. But creation science goes beyond what the evolutionists, where they end. They've got a great theory that explains a lot of things. It simply doesn't explain enough. There are better theories out there to explain the world because the truth is what the Bible says is true about the origin of things. We need to go to the Bible, find out what happened, and then understand the world in the light of it. And if we do, when we do, we can create better theories. with greater explanatory power, greater heuristic value than the secular theories. This is what we ought to do. Thank you.